In this video, I'm going to be going through the HSC Engineering Studies content for Year 12 as part of Chapter 1, Civil Structures, and we're going to be looking at corrosion. So it's worth starting before we get started to talk about why do we care about corrosion? Well, so the big thing we worry about is rust. So I have the song here, Kingdom of Rust. It's got an interesting film clip with a guy he's got some ashes of his mate. Anyway, but what we're interested in is, so steel is the most commonly used metal, and rust is bad when we're dealing with steel. All metals to some extent react with oxygen, but steel reacts very badly with oxygen. So we generally don't find metals naturally. We find them, so steel looks like this. It rusts, and rust weakens the material. It causes it to fail. And steel rusts pretty readily. Aluminium and steel, when they're found naturally as ores. And most metals, because they react with oxygen, when we find them in the Earth's crust, we find them as ores and they have to be smelted. Gold can be found as nuggets. Rarely it's found in ores. But when we're talking about materials, so we're interested in the process that when we have structures, that why, especially steel structures, what causes them to rust. So there's three main ways that we worry about corrosion. And we're going to talk about the processes we use to protect it. Before I go on, I'll talk about, as an engineering material, we talk about both aluminium and stainless steel, that although they do corrode, they form a protective oxide layer on the outside, which means that when they react with oxygen, they don't form the vicious cycle the way steel does. So to my understanding, when steel rusts, it creates a molecule which is larger than the steel molecule, so it continues to break away, exposing new fresh, raw steel to rust and to be exposed to corrosion. And so this creates a vicious cycle, and it causes steel to fail. So we will find that we're a little bit interested in other materials other than steel, but for the moment we're most focused on steel as our corrosion. Okay, so what we're going to start off with is concrete cancer. Just it's worth mentioning that because there's steel in concrete, concrete spalling, also known as concrete cancer, is also a huge problem. So if rust can get into the steel in concrete, it will spread through the concrete, and it can be an enormously expensive, enormously difficult thing to correct. This is mainly caused because of poor vibration, not enough compaction of the concrete, or because the concrete cover was insufficient, there wasn't enough depth of concrete, or because the concrete strength wasn't high enough. Okay, so before we get started, we're going to use a little bit of chemistry, and we're going to use this acronym that you may have heard of in chemistry, which is oil rig. So you might have heard about oxidation and reduction, which is also sometimes in chemistry called redox. And you can see down here we've got crash course, and they're going to talk about redox. So I'll tell the doves that they can go away for the moment. And yeah, I'll put them there. Okay. But if we look at crash course, he says, well, okay, so what's up with these words? Normally when you reduce something, it means making less of something.
What's up with those words?
Yep.
You know what reduction is? Making less of something, and then oxidation maybe.
He goes on to say that, unfortunately, that when when this was first being developed, that they found that the things became lighter because oxygen was escaping, so they were reducing oxygen, they felt. Here we go. Protochemists would make ores by heating and smelting their ores. During the process, they'd become lighter. Okay, so they chose the word reduce. Unfortunately, we can't change it. He goes on to say that there have been people who've tried and failed, but usually once something becomes convention, it's pretty hard to change. You might say, why am I repeating it? That's because I don't want to get copy struck. I mean, Hank Green and his brother, they wouldn't do that, but you never know. Honestly, actually, for what it's worth, in terms of copy protection, this is a total segue. Feel free to hit the skip button if you're watching this as a video. That the two brothers, they use the phrase "don't forget to be awesome." And I watched a video, I don't know why I was watching this video, I guess for copyright when I was doing design, and they deliberately chose not to copyright that phrase "don't forget to be awesome," because if they did, it would mean that they would have to start suing people who use that phrase on anything. So it's really interesting that with copyright law, if you're not actively going after people who use your copyright, you can't just be hands off and say, hey, look, I'm only going to worry about it when people really start ripping us off. You kind of have to actively pursue everyone, and that's why they decided not to copyright their phrase. So, for what it's worth, I do think that the Vlog brothers probably wouldn't actually sue me, but, I don't want to risk the algorithm. Okay, so I have a little bit of notes here, an introduction to galvanization. Not galvanization. An introduction to the Galvanic Series. Okay, so the idea here is that different metals react differently. They have different electrochemical properties. And this is what we want to look at here. This can be measured in different ways. And generally we consider gold and platinum to be the most or the least electrochemically reactive. I was at trivia and I wrote down the word platinum and I got that wrong because the person said it was gold. I stand by platinum as being correct. It's worth noting that graphite is also is even more cathodic. We can see on the other end of the spectrum we have magnesium and zinc. They are the most anodic. We're going to look at what these words mean. So before we get onto that, well, we're going to say that when things corrode, I've got this Pokemon here called Corrodor, and Corrodor here is a chemical and electrical type. Now, I don't think chemical is an actual type, so if I was going to remake this, I'd make metal, because metal's a type, right? So I'd make it metal and electric type. It's also electric, not electrical, isn't it? Anyway, one day I'll pay an artist. Sorry? Steel type. Oh, there you go. Anyway, We're a little way off me commissioning someone to draw art for me to make Corrodor my Pokemon. But in the meantime, Corrodor has 3 attacks. Now, I'd also make Galvanic Corrosion the most powerful attack. So the reason for this is in the textbook they refer to Galvanic Attack. And so I thought when I heard Galvanic Attack, I thought of... I'm going to go to another song. There's a band called Massive Attack. Yeah, we're going to do it. Okay. I can't actually see while I'm typing, so I'm just hoping that this will come out. What's interesting is if you saw the the album for this, the album, it looks rusty. Anyway, coincidence. Okay, so I don't know how me adjusting the screen there is going to affect things. Oh, did I show enough video there that I'm going to get copy strike? Hopefully not. Okay, so we need to protect things. So we have massive attack, or a galvanic attack rather. And so the main attack that our Pokemon uses is galvanic corrosion, right? And maybe it's like a poison effect. Maybe that's why it does less damage. Anyway, we also have concentration cells. I can't even hear my massive attack here. This has got an interesting film clip too. It's all upside down and stuff. Oh, maybe it's just quiet for the start. Yeah, it is quiet for the start. Okay, there we go. Pretty interesting film clip. Okay, so we've got the next one is concentration cells, and then we're going to learn about stress cells. I have a picture somewhere that talks about these. Here we go. Another way of referring to galvanic attack is, what do we use the term? Galvanic corrosion. The term I learned at uni was dissimilar metals. So when you think about this, is if we have 2 dissimilar metals, if we have 2 metals that are not the same type next to each other, you're going to have a bad time. That's actually a meme. I'm going to write that down. A meme idea. Okay, gonna have a bad time. Anyway, I've got to keep talking, otherwise the copy strike will strike. Okay, so what we need to worry about is the Galvanic Series, and what we can see here is that in my excellent drawing here, that if I have a rod of tin, Is tin Sn? I think so. And if I have a rod of zinc, what will happen is that electrons will flow from the zinc to the tin, and that will cause a electric cell to complete. How does the electricity travel through water when water is a covalent bond and covalent bonds don't conduct electricity? Well, you might remember right at the start of year 11 when we were talking about different kinds of bonding, that if you dissolve ions into water, the ions can carry the electric charge. So you can dissolve ions into water, and so some salt, for instance, and the NaCl will become ions, and it will allow an electric charge to complete a circuit, and so electrons will flow from the zinc to the tin, and what will happen is that the zinc will rust. Now, I'm just going to go back to our series just to check that. So tin and zinc. So tin is the cathode and zinc is the anode, and that looks about right. Okay, so now that we've got galvanic corrosion, we've got to worry about these terms anode and cathode. So I've said here that gold, right, gold is going to be the cathode and that zinc is the anode. Now, if that helps you to remember, I remember G and C kind of look the same from their Roman origins. They actually were the same. Julius Caesar, his first name was Gaius, but it's often written as Caius because they didn't have the letter G until a blind engineer put it back. Yeah, so Appia, someone? Yeah, he's got a road named after him. The most famous Roman road in Rome is called the Appian Way. I think, let's see, are we going to go here? No, we're not going to go here. I think his name is like Gaius Appius or something like that. Anyway, anyway, he added the letter G back into the alphabet. Don't quote me on that. I'm no history teacher. Okay, zinc, I remember A to Z. And there used to be ads when I was a kid called Centrum. And in that ad, he'd used to say, complete from A to zinc. So it was a guy called Robert de Costella, maybe? And he used to say, yeah, here we go, from A to zinc. So I think of A to zinc. I think of the anode as zinc, or A to Z. And I remember that C and G, they kind of sound together. Whatever works for you. I will use another analogy, which some kids have got upset about. So gold and platinum, they're rich metals. And you could think that in our analogy where we talk about electrons as being like kids, so we think of like celebrities, really rich platinum celebrities, that they go and adopt other people's kids. Anyway, but that's I don't really like that analogy, so I'm not going to use that too much. Okay, so let's have a look at our... we don't need that anymore. Let's have a look at our two kinds of things. We've got cathodes and we've got anodes. Which ones are which? How will we recognize them? Well, okay, we've got to go back to what we just saw right at the start with Hank Green talking, maybe John, yeah, it was Hank, talking about reduction. Now, so the analogy that the acronym that people use, or the initialism that people use, is oil rig. So they say that oxidization is loss, that's the oil, and reduction is gain, that's the rig. So oxidization is loss of electrons. Reduction is gain of electrons. Now, I like to point out that it's ironic. That will come back later. So what we're going to have a look at here is that reduction is going to happen at the cathode, and the reduction is going to happen at the cathode, and that we know that the cathode is usually expensive metal. So do you see the gold background here? It's very expensive metal, yeah? Gold, expensive metal. So we remember the expensive metals, they're more likely to be cathodes, and we're remembering that reduction is happening there. And it says reduction is gain. It's ironic. And here we have a hipster cat. See, it's a cat to help you remember cathode, and he's a hipster because he's wearing glasses, right? And suspenders and a bow tie. Anyway, when I made this picture, my wife... I'd spent about half an hour making this picture, and my wife, in literally 5 minutes, made a better picture than me. And part of me wishes that I'd kept that picture, but I was so angry that she made a better picture than me in 5 minutes that I deleted it, and now it's gone forever. Anyway, so what we're going to remember is that expensive metals don't rust, right? So they're generally the ones that don't rust, and that's probably why they're expensive, realistically. Okay. On the other hand, we have anodes. And anodes are where the oxidization happens. So we have the angry ox. Now look at that ox. He looks angry, right? So I like to think of, like a country western song. Well, they always talk about how, like, you lose your car, you lose your wife, lose your job. Or the joke actually goes, what happens if you play a country western song backwards? You get your wife back, you get your car back, you get your job back. Anyway, Anyway, in this case, look at this guy. He looks like he's lost his job. He looks like he's lost his car, lost his wife, right? So he's angry, right? This ox, and so we're remembering that oxidization is loss. That's where the ox part of it comes from, and he's lost a lot of things. So it's also, we're going to point out later that the ox is stressed. He's got poor air quality, right? He's got low oxygen, and cheap metals are usually the ones that rust. Right, usually. It's not an absolute rule, but it's going to help us. So when we go back to our galvanic series, here we can see that we're not generally given, here we can see this range of how many volts we have. We're not usually given that. What we're given instead is we're just told an order of materials, and in this case, this is a good example of what you might be given. You might be given something like platinum and gold, and then zinc and magnesium on the other end. I'm going to show you a Hsc question that shows these, but in the meantime, that's probably what you'll get. Now, the thing is, they will not necessarily label the galvanic series for you. So that means you have to have some idea where at least some metals are, so to help you. So if you see gold or platinum, you know that that's going to be pretty good. Graphite, also pretty good. On the other hand, if you see aluminium or zinc, or magnesium on the other end, you know that those ones are going to be the anodes. Right? So we've got A to zinc there, aluminium and zinc, they're the anodes. Copper and gold and... forget the copper, gold and graphite and platinum, Cg is how I remember that. Okay, so what does that mean? Well, I've got a question here, and it says a metal sleeve was used to join two mild steel pipes. After some time, the pipes have corroded as shown. Now, I don't know why we're not replacing the sleeve with another mild steel sleeve, but we're not. So instead, we have to choose another material to use. Now, we can see mild steel on this series is in the middle, but what we want to do is we want to prevent the corrosion to the, so it says here, minimal corrosion to the pipes. We don't want the pipe to corrode, which means that we want instead the sleeve to be the thing that corrodes. Yeah, we want the sleeve to be the thing that corrodes. So what we want to do is we want to make sure that the material we use is damn it. Okay. Damn it. Okay. Yes. I would personally be using one of these materials. I'd personally be using the aluminium or zinc, and I'd be using the aluminium because aluminium is a material, so the aluminium, we want the sleeve to corrode, so we're going to use, which of the following would be used for the sleeve to make sure that it corrodes? So we'd use the aluminium so that the aluminium will be the thing that corrodes, not the steel, and that we want to pick the one that is closest to steel. Unfortunately, this question, the answer was B. Now, there were big arguments on ESNet as to, well, first of all, you don't really want to weld cast iron. You also, you maybe braze it, I don't know. The point is that it's not a very good question. So when you see this question in your review, know that this question was heavily debated. Really what you would want to do is you just want to use the same material. But what we're going to do instead is we're going to talk about what are some other examples? Well, probably the classic example is don't use graphite on external steel. If you have a steel beam, don't write on it with graphite because graphite, we saw, is very cathodic, and it's more cathodic than steel, right? Mild steel, which is right down here. So what's going to happen is that the graphite is going to steal electrons from the stainless steel. Now, probably won't be enough to cause it to fail, but that's why we don't draw on steel with graphite. So you don't use a lead pencil or a graphite, a sharpened pencil. Anyway, that question, I remember that being hotly debated. So I do have the answer here. Question 18 is B. But in my opinion, I've told you why I think that you would want to choose for, we want to ensure minimum corrosion to the pipe. which means that we want the thing that corrodes to be we want a more anodic sleeve, so I would use, and we want to use the one that's closest, so we'd use aluminium. Because this question's so bad, I don't use it in any past papers. It was, like I said, hotly debated in ESNet. Okay, so we're going to go to the other attacks that we can look at here. So we have concentration cells and we have stress cells. So if we go back to corrodor, right, concentration cells and stress cells. So what do they look like? Well, a concentration cell is if you have a small scratch, say in your car paint, what will happen is you'll have an area of high oxygen near the surface. So imagine it fills up with water, because there needs to be something to allow the electrons to pass, and so water is a good candidate there, as long as it gets some ions there. And if we can get high oxygen at the top of the crack and low oxygen at the bottom of the crack, well, where is the rusting going to occur? Where's the anode and where is rust going to occur? Let's think back to our angry ox. The angry ox has low oxygen. So the area of low oxygen is going to be where rust is going to occur. Yeah, the area of low oxygen is going to be the anode, and that's where rust is going to occur. Now, the next one we are going to look at is stress corrosion. So in stress corrosion, so this is why welds are more likely to be rust is more likely to occur at welds, because welds are an area of stress. So if we take an example of this, is if we bend a nail, what we will see is that where are the areas where this nail has been stressed? Well, it's obviously been stressed at the bend. It's been stressed at the top where it's been forged, and where it's been forged at the bottom to be sharp. So these areas are where it's going to be stressed. But let's focus on the high stress on the bend. Well, the high area of stress, that's going to be the anode. That's where rust is going to occur. And the low area, this rest of it is going to be a low area of stress. Yeah? Okay. So let's have a look at some Hsc questions. So this is from, I can't really see the, there we go, it does say that, 2014 paper. In the 2014 paper, it says, other than applying a protective coating, what can we do to protect the steel from corrosion? Okay, well, we haven't really talked about how we're going to protect things from corrosion yet, so we're going to go to the next question, which is here. And it says, we see a nail that's been corroded. It's lying in a polymer gutter. Now, it's important that they say a polymer gutter. If it had been in an aluminium gutter, if you'd left a steel nail in an aluminium gutter, you'd have two dissimilar metals. Yeah? And that would cause the steel, because the steel is more anodic, it would be the one that corrodes. In this case, they've eliminated that by saying it's in a polymer gutter. So identify the type of corrosion and sketch the areas indicating where the anode and cathode areas are. Well, obviously, given that we just talked about this, is going to be stress corrosion. And let's have a look. They've said that this area, and this area, they've all got greater stress, so they're going to be the cathode, the anode, and the cathode is going to be the other two areas, both here and here. Here and here are the cathodes. Okay, so you talked about stress corrosion, so now we're going to talk about ways, how do we prevent, what are the forms of protection that we use to prevent this massive attack? Okay, well, we have sacrificial anodes. So I teach a lot of kids who care about boats. My daughter's going boating tomorrow, so she might have asked the guy who owns the boat to ask, how do you prevent corrosion of your boat? Well, what you have is a sacrificial anode. You have a very anodic material, usually a lump of zinc, and you attach it to the hull of the boat. So you can see that here, the rudder. Yep. Yeah, you can see that you buy. I think you buy them from boating stores. I hear they're like anywhere between $20 and $50, depending on how big they are. But if you have something that's bigger than that, if you have something bigger than a boat, you can put a sacrificial anode on lots of things. But if you have something like a bridge or a pipeline, what you can do instead is you can have impressed current cathodic protection, which is sometimes just referred to as impressed current protection, because all of these are cathodic protection. So it's ICP. There was a bunch of angry clowns in the late 90s, early 2000s called ICP. They also had a song about magnets. Anyway, they were wrestlers. In their concerts, they spray people with soft drink. Anyway, so in this video here, we can see that what they do is that they provide an electrical current, so that way the missing electrons are replaced, and we actually reverse that flow of electrons, is what happens here. So, when we reverse the flow of electrons, we don't have a... I wonder what the difference between this one and this one is. Huh. This one's newer. Grammarly. Oh, who would have thought it? Anyway, I'm going to copy this just so that I have this for future classes. I haven't even watched it. Don't know if it's any good, but better to have it and not need it than need it and not have it. But I did want the picture that went with... Feel free to skip for 5 seconds. Okay, so I've got another question. Oh, let's go back to the previous question here. Okay, so... No, there only is one question here. Okay, did I close that? I hope I didn't close that. 2014. Oh, here it is. Okay. All good. Okay, describe a method other than applying a protective coating that could be used to protect steel from corrosion. So we can see it's a wharf, so it's obviously in a heavily corrosive environment. Now, often when you're building stuff in wharves, you will use stainless steel reinforcement, and you'll use stainless steel as much as possible because it resists corrosion through that protective oxide layer. Because they're saying other than applying a protective coating, what are the other ways that we can protect it? Well, if we look at this, we're going to see that the answers are... I got to go back to the answer. What is it? 21D. 21D. Okay, it's going to say the best choice here. This is too big for sacrificial anodes. But you know what? If you wrote a sacrificial anode, they're still going to give you the mark. As long as you've explained it, right, which is provide a detailed explanation, so that you need to say how the... Well, I mean, I would almost say that was an explain. But in this case here, they've said ICCP, impressed current cathodic protection. It's used to supply the steel with electrons, forcing it to become the cathode, and then thus protecting it from corrosion. This method is generally used in large structures because a sacrificial anode cannot provide enough current to provide provide complete protection. Okay, so yeah, I think that's an explain. I for what it's worth, I would write explain if I was writing that paper, but you know what? When I write a paper, I can complain. So, I've got one more question here. Yeah. Identify the factors that contribute to stress corrosion cracking in aluminium alloy aircraft. So this is really in part 4. We talk about how we can have fatigue corrosion, and that is just another form of stress corrosion, effectively. Let's have a look at their answer. They talk about the high moisture content in so planes fly in the air. There's a high moisture content where they fly, as well as a sustained tensile strength, which can be applied externally, more commonly residual. Yeah. Okay, so what we're looking at here is you got to think that planes, they've got lots and lots of vibration because there's always going to be very small changes in air pressure around the plane, causing the plane to be moving the whole time, moving up and down. There's a lot of moving parts on a plane. So that creates areas of stress, and stress corrosion is more common in aviation because of its the high moisture contents and the high levels of fatigue stress. Okay, so in terms of protective coatings, which the question said we didn't want to talk about, but it's worth mentioning. So protective coatings can include things like painting. So the Harbour Bridge, the Eiffel Tower, they're just being painted. Well, okay, the Harbour Bridge is painted pretty much all the time. I think the Eiffel Tower is painted every 7 years, something like that. It probably doesn't have as much... it doesn't have lots of moving vehicles moving over it, so maybe that's why it doesn't need as much as the Sydney Harbour Bridge does. But beyond paint, well, what we can do is we can provide things like chrome plating. So we have electroplating, and so it's nickel electroplating and chrome plating here. I'm not going to click on those videos because they're kind of long. These are do-it-yourself. See, this is why I don't click on those videos. I don't need to see Mr. Beast. Anyway, if you want to watch those and see the process, they have, the guys explain what's going on. Here we have hot dip galvanizing, which is another coating. This is where we coat we use a electroplating process where we are using liquid zinc, and we dip the steel in liquid zinc. We also use products like zinc alum these days, which is zinc and aluminium. That's a very commonly used product for sheet metal. And if it's coated in a layer of plastic, it's then called color bond, which provides even another layer of protection on top of that. I'm just because it's a bit loud. Anyway, so you can see the material being hot dipped. We can also buy cold gal. So if let's say you find a rusty old gate and you think, hey, this is going to be perfect for my house, but I'm a bit worried about this rust. Well, you can just go and buy cold gal, which can be painted on directly, and it's different to paint because it provides that. Because zinc is anodic, it's going to provide a sacrificial process. It's also worth mentioning that zinc and aluminium, they both provide a oxide layer. Okay, so that will be it for corrosion, and yep, we're done.